Hello everyone, welcome to my channel. And as you all know, we are dealing with the problems, and in this series of problems we have already completed 7 problems, and our topics remain resonance, aromaticity, carbocations, carbene ions. Now in the course of discussion I wanted to bring a very important topic which is called as steric inhibition of resonance, SIR effect. So what is the meaning of steric inhibition of resonance? I will put in front of you in the form of a problem. We will analyze our current problem and then we'll see a very important thing that is called as SIR effect. Okay, so straight away let us come to our question and then we'll analyze. In this current question you can see we have 4 carbocations A, B, C and D. On your screen you can see we have the structures of all the 4 carbocations. Okay, now the question is asking about arrange them in decreasing order of their stability. When you are going to assess their stability, you know the carbocation has got a problem that a plus charge is there, and I have already told you either it be plus charge or minus charge, it is a problematic thing. It is a burden on the species. So how to reduce that burden of plus charge or minus charge is by spreading the charge, is by dispersal of charge, is by resonance effect, is by inductive effect. So many effects we have studied, and we will try to include those things. Now let us try the carbocation number A, and from there we will come up with certain situation. Now I have drawn the carbocation A. Now once you see this carbocation, you immediately realize what is the problem. So you can see first, this is the carbocation number A. As you all can see, this is a carbon, a 3-degree carbon, because with this carbon 3 carbons are directly attached, so it's a 3-degree carbocation. I'm talking about A, and it is directly attached with a benzene ring, as you all can see, and this benzene ring has got 2 tertiary butyl groups at the ortho positions, at the 2 ortho positions. So this is the structure of this carbocation, and I will make more I will give more physicality to this structure in next slide. As you can see, this is what we are dealing in the carbocation A, and this is the benzene ring, as you can see, and there are 2 ortho positions, 1 and 2, and you understand these 2 ortho positions have got tertiary butyl. So you understand this is a carbon which is attached with 3 methyl group. This is also a carbon which is attached with 3 methyl group. It is tertiary butyl group, which I have drawn like this. Okay, now you understand what is the problem in this structure. First let us see where is the plus charge. Once you recognize that this, okay, this is the carbon where the plus charge is there, okay, and this carbon is directly attached with 2 methyl groups, as you can see, and you know that this carbon, the carbocatonic carbon, is sp2 hybridized, so it's flat. Once it's flat, you understand it tries to remain in the plane of benzene ring. So you can understand this is a benzene ring, and this is a carbocation. You understand this is a carbocation. It has 3 valencies and it is a flat particle, and it tries to remain parallel to the benzene ring, okay, in the same plane, coplanar with the benzene ring. So in that course, if it tries to be in the same plane of benzene ring, the problem arises. What is the problem? Because of these 2 bulky groups methyl, as you can see, there happens a repulsion. There happens the repulsion due to their sizes. This tertiary butyl group is also a very bulky group. You can understand it's a very bulky group. Left also and right also, you have 2 bulky groups. and as this carbocation tries to remain in the plane of benzene ring like this, from here one bulky group is there, from here one bulky group is there. So in that motive to remain in the plane of benzene, it encounters severe repulsion. You can see these groups are now fighting for the space. This is called as steric repulsion. This is called as steric repulsion. Steric has to do with the size, and because of the size of the methyl group and the tertiary butyl group, there starts fight for the space. They are fighting for the space because of their bulky size. Now there is a repulsion, and as there is a repulsion, the potential energy of the system increases. It becomes unstable. So what does repulsion brings to a system? It brings instability. Okay, so this particular instability is because of the sizes of the groups, the 2-methyl on the carbocation and the 2 tertiary butyl groups on the at the ortho positions of the benzene ring. Now what to do? So you can understand that because of repulsion the stability has decreased, so it will try to reduce the repulsion. So what is the way it can reduce the repulsion? You can understand in this simple manner. For an example, this is a benzene ring, okay, and this is the carbocation, okay, like this. So if it is remaining parallel to the plane of the benzene, if it wants to remain in the plane of benzene, it encounters severe repulsion because of its methyl group and the 2 methyl groups which are attached at the ortho position. Now, in order to reduce this repulsion, what it can do is it can turn its plane like this. For an example, earlier it was like this, okay, it was like this, and now if it turns perpendicular like this, so it avoids the clashes between the 2 methyl groups and the 2 tertiary butyl groups on the at the ortho positions of the benzene ring. So earlier it was trying to remain adjusted in the plane of benzene ring, but it finds that in doing so, the methyl groups on the carbocation are having a huge repulsion with the bulky groups at the ortho positions of the benzene ring. So it feels that it is a harmful situation. It has to immediately reduce that repulsion. So what it can do, it will just become like this. You understand? As it becomes like this, you understand the 2 methyl group, one goes up and one goes down. One goes up and one goes down, and then it helps in avoiding the repulsion. And I have drawn a figure, as you all can see. This figure I am talking about. So what this carbocation wisely has done, instead of being coplanar with the benzene, it tilted like this. So this carbocation, instead of being like this, it became like this. As it became like this, the 2 tertiary butyl groups from here and from here, they are now not in immediate contact with the 2 methyl groups. Earlier, these were the 2 tertiary butyl group and 2 methyl group were like this, and there was a severe repulsion. So in order to stop that, reduce that, it turns its plane like this. And as it becomes like this, you understand, 1 methyl goes up the plane of benzene ring, 1 methyl goes down the plane of benzene ring, and this carbocation plane becomes perpendicular to the plane of benzene ring. If benzene ring is like this, this carbocation turns like this. So the plane of carbocation now becomes perpendicular, orthogonal to the plane of benzene ring. And how does it help the carbocation? It helps in reducing the steric repulsion, because there was lots of repulsion in the molecule because of their sizes. So it had to do that. It had to change its plane. What is the consequence of the carbocation changing its plane? Is there any consequence? Yes, now it has to pay for reduction of repulsion. Although it has reduced the repulsion, now it has to pay it like this. You understand? The carbocation, if it is, for an example, this is benzene ring, you see, this is benzene ring I have drawn, and if the two ortho position did not it did not has what the bulky tertiary butyl group, then what is happening, this carbocation is able to remain parallel to the coplanar with the benzene ring, because you understand there is no one to put a problem, because ortho position both are empty. Now in that case what happens, this carbocation remains in the plane of the benzene ring. So what is the goodness of that remaining in the plane of benzene ring? You can understand like this. This carbocation, as I have told so many times, has got a vacant orbital. You understand? It has got a vacant orbital. How does a vacant orbital come? You understand, carbon has normally 4 electrons in the valence shell, where in neutral carbon you have 4 electrons in the valence shell. Out of that, 1 electron is taken away, it becomes carbocation. Now it has 3 electrons. Once it has 3 electrons and you see its valence shell configuration, 2s 2p into, now it has 3 electrons, 1 electron remains in 2s and 2 electrons remain in 2p. So if you draw the electron box diagram, it will be like this: 1 electron in 2s and 2 electron in 2p. Once you do this, you understand 1s and 2p becomes sp2 hybridized, leaving 1 p orbital vacant. So it has 1 vacant p orbital, and that vacant p orbital, by remaining in the plane of benzene ring, the carbocation, by remaining in the plane of benzene ring, it helps in getting this vacant orbital parallel to the pi system. You understand, this is a benzene ring and it has got 3 pi bonds. As you can see, these are the 3 pi bonds, and these pi bond, as you can understand, have been made because of the overlap of the p orbitals. As I have mentioned, you can see how the p orbitals have overlapped sideways to make these 3 pi bond. Now, if the carbocation remains coplanar with the benzene ring, it makes the vacant p orbital parallel with the pi system and all these 6 p orbital of the benzene ring, and this vacant orbital, all 7 orbitals remain parallel to each other. So if you imagine this is a benzene ring, so it will have 6 p orbitals like this, and the carbocation here also gets its p orbital parallel to the p orbitals, 6 p orbitals of the pi system. And if it is possible, there is a conjugation, there is a possibility of resonance. And how the resonance possibility happens, you understand, it is very simple to see. For an example, if I draw a diagram like this, these are the 3 pi bonds and this is a carbocation, you understand. In this carbocation, if you see the possibility plus, single, double, single, double, single, double. So there is a complete conjugation. Okay, the plus charge can now be in resonance with the pi bond and it can be delocalized inside the ring because there is a possibility of conjugation. But how that possibility comes, you should realize. It comes because the vacant p orbital of the carbocation is able to remain parallel with the pi bonds of the benzene ring, pi system of the benzene ring. That is the condition required for the resonance to happen. Now, if for an example, because of the bulky groups, now if you attach the bulky groups at the ortho position, now you have attached the bulky groups at the ortho position. So if you attach the bulky groups, now these are the bulky groups. As you attach these bulky group, to avoid the repulsion, these two groups have now became perpendicular to the plane of the benzene ring, because if it tries to remain in the same plane, there will occur a severe repulsion between the groups attached with the carbocation, the 2-methyl, as we have already seen in this diagram. Such situation will come, and it does not want that this situation comes because repulsion is heavy. So to avoid that repulsion, it turns its plane, and as it turns its plane, the one goes up, as you can understand, one goes up, one goes down, and now you can understand this is a plane, 1-methyl and this carbon, it's a plane which becomes perpendicular to the benzene ring, and as it becomes perpendicular, the p orbital, the vacant p orbital now becomes perpendicular to the pi system also. Okay, so as this p orbital, the vacant p orbital becomes perpendicular, this was the pi system, and earlier the vacant orbital was parallel. This was the pi system, 6p orbital making a pi system, and this was a vacant p orbital. Earlier, in the absence of crowding effect, all were parallel to each other, and there was possibility of conjugation, resonance, stabilization. But if there are two bulky groups at the ortho position, if they, because of the repulsion, this carbocation becomes perpendicular to the plane of the benzene ring, simultaneously this p orbital also becomes like this. So as the carbocation tilts its plane, the p orbital also tilts its plane, and now the pi system is as it was earlier. Earlier the p orbital was like this, but as carbocation turns, the vacant p orbital becomes like this, and it is perpendicular to the pi system now, not parallel to the pi system now. It cannot make the pi bond now, because to make the pi bond, to be in conjugation, to avail resonance, the orbital should be parallel to each other. But to avoid repulsion, as the carbocation turns its plane, the vacant p orbital also tilts and turns perpendicular to the pi system, and there is no more conjugation. So you should understand from this behavior that this particular condition, this particular carbocation will change its plane and will remain perpendicular to the plane of the benzene, and in that case the vacant p orbital is now not parallel to the pi system, and in that case the conjugation cannot be availed, so there is no possibility of resonance. Is it okay? So you should keep in your mind. So once I come to the four carbocations given in the question, let us try to assess each one by one now. Now, A, you understood from the previous discussion that because of the bulky groups attached to ortho positions, this carbocation will turn its plane perpendicular to the benzene ring, and as it does, the vacant p orbital is no more parallel to the pi system. The conjugation is lost. The chance of resonance is now no more, so there will be no resonance, and this resonance has been lost because of the steric repulsion, because of the sizes of the group. So we call it steric inhibition of resonance, SIR. Why we call it steric inhibition of resonance? You understand, steric means because of size, inhibition means you have not allowed what? Resonance. So because of steric bulk, because of size issues, the resonance is not allowed. Why it is not allowed? Because in order to reduce the repulsion, you turned your plane, and now the vacant p orbital is not parallel to the pi system, and that you have done in order to avoid the steric problem, steric repulsion. But in that case, you have lost the chance of conjugation, you have lost the chance of resonance. So because of SIR, there is no resonance, no resonance. So this carbocation lacks resonance. What next you can have to stabilize this carbocation is just these groups, these tertiary butyl group have got plus I effect. What they have? they have got plus I effect. It means these alkyl group pushes electron via the sigma bonds. So via the sigma bonds, you understand, they are going to give electrons, and this plus charge will be satisfied just because of the inductive effect, the plus I effect of the tertiary butyl group. And on one hand they are giving electrons through inductive effect, through sigma electron, and on the other hand they became the culprit. They were the culprit for not allowing the resonance to happen by turning the plane of carbocation, by making the carbocation to turn its plane, SIR effect. So the only relief this carbocation has is because of the inductive effect of the two tertiary butyl groups. Now if you come, so it has the SIR effect, that is no resonance, and plus I effect. So now coming on to the case B. Now case B, you understand, the ortho position is not having these bulky group. It is just having the very small hydrogen atom that has nothing to do with the steric problem. Okay, so these groups now are far away from these two methyl groups, and these two methyl groups are now not having that problem which A had. So they will remain parallel to the, they will remain coplanar to the benzene ring, and as they remain coplanar with the benzene ring like this, their vacant p orbital remains parallel to the pi system of the benzene, and as they remain parallel to each other, there is all possibility of conjugation, resonance, delocalization, and you will make the resonating structures. As you will keep the plus charge, as you will draw the resonating structures, I have told you how to draw the resonating structures. You will see that 3 resonating structures you can make by delocalizing the charge inside the ring, and you see the plus charge is now distributed, it is now spread, delocalized, and it gives the stability. So what are the merits of the structure B? It has resonance also, and it has plus I also. Why plus I? Because that remains with the tertiary butyl. That is an effect that it delivers through the sigma bond. So it just pushes the electron through the sigma bond, both the tertiary butyl group, and from there the plus charge gets really whatsoever it gets. Okay, now coming on to the case C. Case C, again you find that the two ortho positions are devoid of any bulky groups. So the two positions are not having any bulky group, so there is no problem of SIR, steric inhibition of resonance. So this plus charge will easily go inside the benzene ring, will delocalize the same number of resonating structure you will get as you will get in the case B. And again the tertiary butyl group, two tertiary butyl group you have, they will exert the plus I effect, and you will have the plus I effect of the two group. Okay, in that sense B and C, there is a tie in the effect. Both have got resonance stabilization, both have got plus I stabilization. Now coming on to D, you should understand what is the problem. The problem is it has one group, you understand, at the ortho position. Now what is the problem? If you again see this picture, here you have the two groups. So let me make it clear. So here you should understand what is the possibility. Either you have from one side, okay, either you have a group from one side as you have, or you have two sides. If you had a group from one side, for an example, if I rub this, okay, then also it has the same issue. It will happen from one side. So this will always be in problem. So in order to reduce the problem, it will again try to go away, and as it tries to go away, again it has to do only one possibility. It will turn like this. It will go away from the planarity, and as it turns out as it goes perpendicular, again the conjugation is lost, the vacant orbital becomes perpendicular to the pi system, and again there is SIR, there is no resonance because of steric issues. Either you put one bulky group or you put two bulky group, both will introduce this situation SIR. So if you come to analyze what we have been doing, the D option, so D is subjected to SIR first of all, and second thing, it has plus I as usual. These are the two bulky groups, and these bulky group will give electrons through inductive effect. So now we are in position to finally correlate the merits and demerits, and will get one hierarchy. Okay, on our screen, let me clear the things, and will now give the final verdict on the stability. If we come to the final verdict now, so you understand what is the final verdict. If you compare the resonance effect and the inductive effect, let me give you the answer. Resonance is a dominating effect in comparison to inductive. So if resonance is a dominant effect, especially when the atoms are belonging to same period, second period, and all are belonging to the same second period, so resonance is a dominating factor. And if you take resonance stabilization, then that stabilization is present just for two options, the option number B and the option number C. A and D both are devoid of resonance stabilization, so obviously A and D are going to be on the rear side, they are not the leaders, and B and C are the superior carbocations. Now if you try to compare between B and C, so you have to understand the inductive effect. For an example, if I say inductive effect, so you should understand inductive effect is a function of distance. If you see in the case of B, the two tertiary butyl group are meta position, the two meta position. So they are nearer to this carbocation, and as the group is nearer, it can give more through inductive effect, because inductive effect is a function of distance. As you increase the distance, you understand its effect, its help is reduced drastically. So on that account, if you think the two tertiary butyl group in the case B are nearer, and in the case of the C, one is the same distance, but the last one is far from the carbocation in comparison to B. On that ground, you can say that the C is a better option than B. So if we try to now put the hierarchy, C comes first, then will come the B, and now it is turn of comparison between A and D. Now A and D both are devoid of resonance, so resonance is not going to play the decisive role here. Okay, so what is going to be the decisive in these two cases is going to be the inductive effect. And as you can understand, in the case A, the two tertiary butyl are nearest possible to the carbocation, so they can help through inductive effect in most advanced manner, in the most in the highest manner. Okay, and in the case of D, you understand one is the same distance as the A had, but the one is the farthest distance, the para position, where the inductive is going to be very less in comparison to A. So on that basis, you can now put your hierarchy completed. After B will come A, and then will come D. So this is the order of stability, and we have come to this conclusion after pondering over several issues. The very important issue which I want to emphasize was steric inhibition of resonance. We saw that A and D, although theoretically you could see plus single double, but theoretically it was seen, if you see practically, there was no conjugation. Basically there was no condition fulfillment. The conditions were not fulfilled, the orbitals were not parallel, and to avoid the steric repulsion, the carbocation tilts its plane, becomes perpendicular to the benzene ring, and there is no overlap possible now. And when the overlap is not possible, there is no delocalization of charge. So A and D certainly had that disadvantage, but B and C did not suffer from that disadvantage, and we decided just based on inductive effect. And for inductive, you have to keep in your mind tertiary butyl has got the tendency to give electron through getting the sigma electron towards you. Okay, it shifts the electron towards you through the sigma electrons. And if you be nearer to the carbocation, the effect of inductive effect will be more, and as you go away, the inductive effect dies away very rapidly, and that is the problem with the D, because no resonance, and inductive also not that much as was present in A. So that is how you have to think, keeping the things clear in your mind. Just for the sake of conjugation, you should not see it, that plus single double. You should also keep in your mind whether the orbitals are actually parallel or not. If it is not because of the issues like steric inhibition of resonance, you should not go with the resonance possibility. Okay, that is all about the steric inhibition of resonance, and more to come in the coming videos. We'll take up steric inhibition of resonance with different cases. Till then, take a good care of yourself. I hope you all must be enjoying my videos. Thank you very much.